All righty, folks. So we got our final bit on dealing with chapter 3. So we're going to see if we can't walk through it. So our last little thing is called optimization. Essentially, it's word problems dealing with relative and absolute extremities. So it's not like word problems dealing with implicit derivatives at a related rate. These are word problems that deal with extrema. Majority of the time it's absolute extrema, but every once in a while we're going to be dealing with this idea of relative extrema. So let's take a look here. Go ahead and read it. Draw yourself a picture and see if you can't figure out what it is we're dealing with. Go and pause the video. All right, let's see how we did here. So we're building a pen. And it's going to be built on the side of a barn. So that means I'm only going to fence in 3 sides. So I can go ahead and draw a picture that kind of relates to that a little bit. Let's see here. There's going to be like my barn, and I'm building a pen. So there's only 3 sides available. Now with that means I have 2 horizontal sides and I have 2 vertical sides. Or 1 vertical side, sorry about that. And it tells me that I have 120 feet of fencing. So 120 feet of fence. So if I add up all 3 of these sides, then I have, that's going to be equal to 120. So 2x plus y equals 120. So I'm trying to maximize the area, find the maximum value of the area. What's my maximum area going to be? Well, area is base times height, or x times y. Now, for our purposes here, you need to realize we really want to try to only be in one variable. So if I can get rid of that y value, I'd be in great shape. So we can actually do that. Y equals 120 minus 2x. And if I plug that in there, now instead of having area, I have area as a function of x. So a of x equals x times 120 minus 2x. So now, if you notice here, we have nothing more than a parabola. And I want you to think of this parabola for a second. By the way, if you wanted to, you can multiply that out. I'm going to do that real quickly. If you think about this parabola, it's not going to be going on forever, right? We're not dealing with, and what I mean by that is we're not dealing with every single x value on this domain. Because if you notice, this parabola has a negative a value, -2. That means it opens down. So if I were to look at the graph of this real quickly, I'm going to make a real rough sketch of this here. I just want you to see what it is we're looking like here. I'm not dealing with the full domain because this graph's going to come up. It's going to cross the x-axis, and then it's going to come back down. I'm not dealing with those values below the x-axis. I'm only dealing with values above the x-axis. In other words, this is a closed domain. So I'm going to be only between those x-intercepts. So those x-intercepts, if I set my 2 factors equal to 0, I find out that my x-intercepts, the domain I'm on, is between 0, because x equals 0. When I set 120 minus 2x equal to 0, I'm going to be equal to 6. So I'm somewhere between 0 and 60. So I'm trying to find the maximum value between on a closed domain. Is that an absolute extrema or is that a relative extrema? It'd be absolute, right? So we're going to go through and we're solving essentially an absolute extrema problem. So we start off, we're going to say what we're going to do, and then we're going to do the work. When we're done, we're going to say what we found. So absolute extrema, or the maximum area, I want to put it in context today. The maximum area of the pen will be located at x equals 0, x equals 60, when f prime of x equals 0 or f prime of x is undefined. So I've given myself permission to go through and deal with the derivative. So I'm going to deal with the derivative of this problem. So I've said what I'm going to do. Now I'm going to go through and do the work. So I'm finding the absolute extrema for this parabola. And I don't care about the absolute minimum. The absolute minimum is going to be 0. I want to know when the absolute max will be. And notice, before we'd have to like graph on our calculators in pre-cal, or we'd look for the vertex. It's all still the same, but if you notice, it doesn't really do anything really all that much for us, because with the derivative, we can just do the same thing every single time. So we take our derivative, we set it equal to 0, whoop, minus 4x. 4x equals 120. X equals 30. That means I have one critical number on my closed domain. So we're going to go ahead and we're going to figure out a of 0. And these are really, really trivial as far as being on an absolute extrema here at this. Because I already know that when I plug 0 and 60 in, my area is 0. So it doesn't really matter on those ones. But I do need to know what it is when I plug in 30. So if I plug 30 back into my equation, I will end up with, in this case, 1,800 feet cubed, or feet squared. And since I asked you for the dimensions, not just the maximum value, I also need to go ahead and figure out what that y value is too. So I'm going to do that real quickly, just so I have it. So y of 30. So 120 minus 2 times 30. That would be 60. So we said what we're going to do. We went through and we did the work. So when we're done, we are going to say what we found. Oh, so sad. Today is pretty much our last day of singing that song, friends. So you're like, thank goodness. Oh. All right. So the maximum area for the pen would be 1,800 feet squared. The pen would have dimensions of 30 feet by 60 feet. And there we go. We just make a comment of what we ended up finding out. So we said what we're going to do. Let's come back here. We said what we're going to do. Wrong color. And then we did the work. And when we're done, we say what we did. All right, well, we've got a few of these to try today, so let's move on here. All right, friends, why don't you guys go ahead? Same kind of idea. I'm going to add a little bit more to it. So pause the video, and see if you can actually set it up. So pause the video, set up the problem. That's all I want you to do. Just pause it, set it up. All right, so we have two same size pens, and they share a side. So let's see, how did we set it up? Two same size pens, and they share a side. So that means both these are congruent rectangles. May not be absolutely congruent, but congruent rectangles. They share a side. So that means Whatever this is, that's what this is. So I have 4x's here, and then I had 4y. And let's see here. We were told we had 200 feet of fencing. So that meant 4x plus 3y is 200. What are the dimensions of one of the pens? Oh, okay. That will result in the pens having the largest area. Determine the maximum value of one of the pens. Notice 1, 1. All right, so I'm dealing with just one pen, even though I'm setting up 2. I'm really wanting just 1. Because if I know what the area of 1 is, then I actually know the area of both. Just double it. Okay, so I'm really only maximizing just one of the pens. So I can stick with this x times y. Now, if I was dealing both pens, it would be 2x times y. In this case, I'm dealing with just one, so x times y. So we got to get our y value by itself here. Because just like before, we want to make sure that we have it in terms of one variable whenever possible. In an optimization, you want one variable. Okay, so let's plug in our area. I have x times, and I'm going to break up that into 2 fractions there. 200 over 3 minus 4/3 x. So, and I should add an a of x up there. I probably should add that in there real quick. So we have 200 over 3x minus 4/3 x squared. And just like before, you want to make sure you get those domains. So if you set your two x-intercepts equal to 0 there, you can figure out what our domain is. So I know I'm going to be between 0 and if I set 200 thirds minus 4/3 x equal to 0, that will give me a domain that's equal to 50. So I'm between 0 and 50. That's my closed domain. So I'm dealing with the maximum area on a closed domain. So that would make it an absolute extrema problem. So we say what we're going to do. The maximum area will be located at either x equals 0, x equals 50, f prime of x equals 0, or f prime of x is undefined. So what we're going to do, now we go through and we do the work. So giving ourselves permission again to take a derivative. I think these are a little bit easier to do than our related rate word problems. But again, it's just something else to look at. So we take our derivative, set it equal to 0. Eight thirds x equals 200 thirds. So that means x is 25. So f of 0, if I were to plug that, f of 0, no f of 0 here. Let's try that again. A of 0. If I plug that in, I'm going to end up with 0 here. If I plug in a of 50, also would give me a pen equal to 0. But if I plug in that 25, I would get an area that would be equal to 2,500 over 3. Otherwise, 833 1/3 feet squared. So that'd be the area of just one of the pens. If I wanted to find them both together, I'd double it. And they asked for dimensions, so I got to figure out what that y value is as well. So we plug that 25 in here, just get that y value that's associated with it. So 200 minus 4 times 25, all over 3, and we end up with 100 over 3 feet. Okay, so we said what we're going to do. We did the work. So when we're done, we're going to say what we found. So here we go. Say what we found. The maximum area of 2,500 feet squared will be located, will occur for a pen of 25 feet by 100 over 3 feet. So one final time, because we only got to say this just a couple more times this year. We say what we're going to do. Then we come back. We do the work. And when we're done, we're going to say what we did. Say what we found. All right, well, that's 2 down. I think we got a couple more to go in us today. All right, let's move on here. Woo. All right, now, notice, this one is dealing with a cubic. Now, quick timeout here. Just like we ended up restricting domains for those that were quadratics, realize we're also going to be restricting domains before a cubic. In other words, say I'm coming up here. When you're restricting your domain for a cubic, realize we only want this first area that kind of looks like a quadratic. Reason being, any value outside of that range, any value outside of that range is going to give me a negative length somewhere. It could be a negative height, a negative width, a negative height, negative length, negative width. So I need to make sure that when I do this, my domain is always going to be in between the 2 smallest x-intercepts. So let's just take a look at what's going on here. I have some 30 by 30 foot, 30 by 30 inch piece of sheet metal. And what is it said we're going to do here is we're going to cut off the same length from each side. So I'm going to cut X in here, and I'm going to cut X in on this side. I'm going to cut X in on this side, and I'm going to cut X in on this side. So I'm going to take this piece of sheet metal, and I'm going to cut it in. So when we go through and we remove out those squares, I'm going to be left with just this side here. So this was 30 inches to begin with. I cut off 2 x's from both sides, so that would make it 30 minus 2x. And if I did it from the other side, that would make this over here also 30 minus 2x. And so those heights of our box is still x by x. So I still have those x's hanging out there. Now, at that point in time, it says we're going to fold up the ends of the box. So that means my height of my box is some x, 30 minus 2x. I create an open-ended box. Not gonna lie, I was pretty proud of myself for making these drawings this weekend to try to help illustrate this. Well, friends, see if you guys can set up an equation and find the domain for that equation for us to be able to figure out the maximum volume. Why don't you guys go ahead and pause it, and we will talk here in a second. All right. When you guys know volume, it's length times width times height. So volume is, the height is easy to find, and the length and the width, well, they're the same. So 30 minus 2x and 30 minus 2x. Now I could write this as x times 30 minus 2x squared if I wanted to do a product rule and chain rule. But I actually, a lot of times, I like to go through and multiply it out just to keep it in terms of just a straight power rule. You don't have to do that. It's just something I do, makes the algebra a little bit easier later on. So when I were to multiply it all the way out, I get 900x, sorry, minus 120x squared plus 4x cubed. And now, just like we said, what are these domains? Now, if I were to go and graph this particular problem here, notice that I only have 2x intercepts anyways, and it makes it a little bit easier because I'm going to hit and I'm going to bounce back right there. So it makes it a little easier to see where those 2x intercepts are when I'm restricting my domain. So I'm going to be between those 2x intercepts. Can't have anything outside, otherwise I'm going to end up with a negative length or width or something somewhere. All right, so we're going to be between then. Our domain will be between, got to make that a little smaller again, whatever makes these values equal to 0. So that means our domain then is between 0 and 15. So again, closed domain, and I'm looking for a maximum value. Once again, it is an absolute extrema problem. So here we go. Why don't you guys actually try it yourselves this time? See if you can work it all the way through. So pause the video, give it a shot. All right, let's see how we did here. The maximum volume can exist, will exist, at x equals 0, x equals 15, when f prime of x equals 0, or when f prime of x is undefined. All right, so we said what we're going to do. Now, friends, we are going to go through and do the work. So v prime of x (900) minus 240x. We're getting some big numbers. Plus 12x squared set it equal to 0. And I think I can factor out a 12 out of that, actually, to tell you the truth. And I'll rearrange the terms while I do that as well. So that would be a minus 20x there. And that would be at 75. So that means 0, 12 times x minus 5 and x minus 15. So x equals 5 and x equals 15. So we are only going to choose the values that fall in our domain. So they have to fall in our domain. So x equals 5 falls in our domain. Technically, x equals 15 falls in our domain, but that was already an endpoint, so there's no sense bringing it with us a second time because I already have it right there. Now, a lot of times, if we have 3 different x-intercepts, a lot of times that'll fall out of our domain and we'll just toss it. So just be aware of that. So there'll be a lot of times we will just let it go. All right, so we're going to plug in our domains here. We're going to figure out where our maximum value is. So that'd be 0. And if I plug 15 in here, that we know that's also going to be 0. But when we have this value of 5, that apparently gives us the maximum volume of our box. So if I plug 5 in there, I'm going to end up with 2,000 on the dot inches cubed. And then just for the fun of it, friends, we don't have to, but I'm going to do it anyways. They didn't ask us to come up with the dimensions of the box, but I'll still do it. So if I take my 5 and I plug it in there into the other dimension, I don't know why I made it y. I did, I guess. Here, we'll help out with that. So times 5, we end up with 10. And 30 minus 10 would be 20. So, we said what we're going to do. We did the work. So now that we're done, we're going to say what we found, friends. The box will have a maximum area of 2,000 inches cubed when the height is 5 inches and the length and width are 20 inches. All right, so say what we're going to do. Go through and do the work. And when you're done, friends, you got to say what you did. All right, we got one final problem here. One final problem on the day. Determine which points on the function are closest to y squared minus 4. Or on y squared minus 4 are closest to 0 and 1. So let's see if we actually can figure out what this even looks like. We got a graph. Now this one's going to be just a little bit more different, a little bit different. So I have some graph, some parabola, and we're trying to figure out when this graph right here will have some point that's the closest. Now realize it's symmetrical, right? So the points we're going to find, there's probably going to be a couple points that are going to be the closest to this point. So there's going to be a couple points here that we're dealing with. But realize that this parabola also goes on forever. So this actually is a relative extrema problem. This is not an absolute extrema problem. Now I don't know what these points are. I'm just going to call them X and Y. But what I have to do is I have to figure out what this minimum distance is right here. I'm not looking for a maximum distance. I'm looking for a minimum distance. So back in integrated 1, or might have been geometry if you're watching this from geometry, or we learned something called the distance formula. It's an offshoot of the Pythagorean theorem. It says the distance between 2 points is the distance between the x's squared plus the distance between the y squared, and then you take the square root of that. Again, it's just an offshoot of the Pythagorean theorem. So if that's the equation we're going to deal with, in other words, I'm going to be plugging numbers into this equation. Now there is going to be no domain here because it's a relative extrema. So I'm going to be taking my x value and I'm going to subtract it from that x value of my point I'm dealing with. I'm using x because x, y, that could be any point along this parabola. I don't know what it is, to tell you the truth. Plus, we have y. No, that's not true. I know what the answer is going to be ahead of time. Maybe did this one before I actually got logged on this morning. So now we have a derivative, or not derivative, we have a distance that's x squared plus y minus 1 squared. Now, friends, when we're dealing with absolute extrema, we only want to have one variable. So we need to get rid of either x or y. And since this is math, you know we like x's. So I do know that what y equals. So if I were to go and plug it in, I end up with x squared plus x squared minus 4 minus 1 squared. So we're doing just a little bit of setup here to help us out here on this one because this is just a little bit more than normal. And by the way, once I plugged in that, x squared minus 4 in for y, I'm now a function of x. I probably should have d of x here. So I am going to kind of combine this a little bit to make it a little easier on myself. So I have x squared plus x to the 4th plus 10x squared minus 10x squared, excuse me. There we go. Oh man, I erased the wrong thing, didn't I? All that and I erased the wrong one. So plus x to the 4th, we'll try this again here. Minus 10x squared plus 25. So d of x equals x to the fourth minus 9x squared plus 25. All right, so that's going to be the equation that we're going to try to deal with a relative extrema over. So, friends, go ahead and pause the video here. You guys know how to do relative extrema. See where you can take it from there. All right, let's see how you did. The closest point to 0, 1 can occur when f prime of x equals 0 or f prime of x is undefined. So we're not just writing it, we're kind of giving it a little bit of context so we know exactly what it is we're trying to accomplish here. We said we're going to do. Now we're going to go through and do the work. So I'm going to take a derivative. Whoop. Oh, that's going to be, actually before I take the derivative, let me rewrite that. So I'm going to be using the chain rule here. So what d of x is, I'm going to get it out from being a radical and write it as an exponent. And if you notice here, I'm going to have an inside function and I'm going to have an outside function. So you can kind of see how we're doing a chain rule to this problem here. So we will end up using a chain rule when we go through and do our derivative. So d prime of x equals outside function. So I'm going to drop the 1/2 down. Subtracts 1 from it. So x to the fourth minus 9x squared plus 25 times the inside function, which would be 4x cubed minus 18x. So we're going to set it equal to 0. And as we set it equal to 0, I'm just going to take the stuff that should be in the denominator and put them in the denominator. So 4x cubed minus 18, that's going to be the numerator. And then the 2 down here. And I'm going to take that negative 1/2 and turn it back into a square root. So this numerator, this is going to be when my derivative is equal to 0. My denominator, this is when my derivative is undefined. Well, friends, we got some very, 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 very good news for you all. If I were to use the quadratic formula on this denominator, this part right here, turns out there's no real solution. It's imaginary. So we don't have to worry about anything that is going to be undefined here. We just got to deal with the top part. It makes the algebra a little bit easier. So 0 equals 4x cubed minus 18x. And for the fun of it, I'm going to go ahead and factor out a x. Yeah, I know I could have factored out a 2. I just didn't want to. Because I'm going to go ahead and do the difference of squares here. Some of you are going, it's not a perfect square. Everything's a perfect square. You just cheat the system a little bit. So that means I have critical numbers at 0. I have one at root 18 over 2. And I have one at a negative root 18 over 2. And by the way, just in case you're curious, that is root 18 over 2 is about 2.12132. 1, 2, 1, 3, 2. I maybe actually drew those dots in the right spot after all. All right. So I'm going to go and test our values here. So let me see. I'll use black here to make it show up a little bit better. X equals a negative 18 root 2. And we're going to plug these in here. We're going to test the intervals to find out, do we have any relative maximum or relative minimum? Whoop. We're just going to plug numbers in each of these intervals to test them here. And just for the fun of it, I'll use -3 out here then. I use -1, 1, and 3. So when we test our values, turns out I end up with a derivative that is less than 1. Why am I using F? I'm using D today. And then when I plug in -1, and then I end up with less than 0, then I end up with a derivative that is greater than 0. So you can already see the 2 points we talked about that would have been the relative mins. That would have been right here. There's a relative min. And then there's also another relative min. And by the way, just for the fun of it, if you notice, when x equals 0, this right here, that would have been a relative max because it's going away from the point. That's as far away as we can get from that point. That's the y-intercept, a vertex, and then it starts coming back to it again. So this was technically a relative max. But we can see our 2 relative min values. So we're going to plug them back into our y. And let's see here. If I plug root 18 over 2 back in for y, I end up with root 18 over 2 squared minus 4. Which is 1/2. And by the way, friends, that's the same value if I were to plug in a negative root 18 over 2. All right, so we know the 2 closest points then. So the last thing for us to do in this chapter, for that matter, is to say what we found. The points closest to 0, 1 on the function y equals x squared minus 4 are the points, I'm going to need to use that decimal, I think, 2.12132, comma 1/2, and positive 2.12132, comma 1/2, because d prime of x changes from d prime of x less than 0 to d prime of x greater than 0 at x equals -2.12132 and x equals 2.12132 as well. All right, and just because we have to do a 1 final time, remember what we did? We start off and we said what we're going to do. We did the work. And when we're done, we say what we found. All right, friends, that completes chapter 2. So we are in great shape here. We are looking good. And I will see you guys in the morning and we can talk a little bit more about this. All righty, take care.